Are you able to see my screen?
Not yet, Mr. Ali. Not yet.
Oh, not yet. Okay. Can you see it now?
No, not yet.
Not yet.
Now we can see your screen.
Okay.
Mm-hmm.
And I'll just put it. Okay.
We can see the screen, but the PowerPoint, not yet. The slides, not yet.
Not yet. That is strange.
Yeah, now we can see it. Just to
Okay.
put it full screen. Yeah.
Yeah.
Thank you.
Mm-hmm. Okay, now we go to the next topic, and this has to do with life cycle well integrity of CO2 storage wells. And we're going to talk about well integrity. And again, I want to thank SPE and IADC, the North Dakota student chapters, and Habib and Nadia and all the section officers for giving me the invitation to speak today. I presented this earlier at other SP and IADC events, and I've just modified a little bit to fit into the time frame that we have for today's presentation. We'll talk about a little bit my outline. What is the definition? Its importance from a life cycle perspective, and my focus is more on the casing design and the primary cement design and the material selection for the tubulars and completions. And finally, we'll end up with what we call the P&A phase as far as the life cycle is concerned. And this slide I had already presented earlier that gives all the global CCS projects. So I won't, talk about that too much in this presentation. Well integrity, the definition. It's here. This is the NORSOK standard. NORSOK is the Norwegian petroleum, regulatory agency, and it's pretty well accepted globally. And then you also have the API RP90 definition. The application of technical, operational, and organizational solutions to reduce the risk of an uncontrolled release and or unintended movement of well fluids throughout the life cycle of a well. The ISO definition and alternative definition is the containment and the prevention of the escape of fluids to subterranean formations or to the surface. So if you were to ask a layperson, what is the definition of well integrity, he or she may say, just keep your production or injection fluids within the pipe, and then you're fine. The NORSOK standard is a functional standard, and it sets the minimum requirements for the equipment solutions to be used in a well, leaving it to the operating companies to choose the solutions that meet the requirements and to fully comply. So let's say you're an operator X working in the Gulf of Mexico. Your well integrity standards may not be exactly the same as operator Y, but it's up to each operator to make sure that the requirements are fully complied with, rather than mandating that every operator should have exactly identical standards. I'm differentiating here between well integrity and wellbore integrity, because to me, wellbore integrity could include borehole instability. And that is when the open hole interval does not retain its gauge and or structural integrity due to hole closure narrowing or washouts or fracturing, collapse, etc. So what happens is mechanical borehole failure occurs when the stresses acting on the rock exceed the compressive or tensile strength of the rock. Shales are the ones that cause most well instability form, and more than 75% of all formations drilled are through shales. So shale instability can be due to mechanical reasons or chemical, resulting from the shale fluid interaction. So it's important to prevent shale hydration and dispersion. And that's the reason why we use oil-based muds and synthetic-based muds instead of water-based muds. How do you prevent borehole instability? You maintain the proper mud weight. The borehole fluid must be compatible with the drill formation. Use proper hydraulics to control the equivalent circulating density. ECD is very important, in order to avoid kicks and losses, especially where there's a narrow window between your frac gradient and your pore pressure gradient. Because always remember, when you're drilling, you're operating within this window between your pore pressure and the frac gradient in order to reach your target zone and not have downhole problems. So that's the reason why I differentiate between well integrity and wellbore integrity. Why is well integrity important? Here are a couple of instances of blowouts that occurred with CO2 EOR injectors. And the one on the left is where was a workover going on in order to clean out the fill. And on the right, it shows the effects of cooling, which results during the expansion when pressure containment is lost. So when pressure containment, this is reference a World Oil article and Les Skinner. And it's a very good article on dealing with potential loss of well control, especially during well interventions. When pressure containment is lost, two processes occur simultaneously. The first is the CO2 is converted from supercritical to vapor with significant expansion and increases with decreasing confining pressure as it moves uphole. Flow behavior is almost explosive in its violence and is not expected by field workers, causing a blowout in a matter of seconds. And basically, you have loss of well control, because always remember, safety is number one, and you want to make sure that you do not have a loss of well control incident at any time. So the unique phase behavior of CO2, and we'll be talking that in the next slide here, leads to high flow rates, which complicate surface intervention work. And the CO2 and produced fluids can collect in the BOPs, in the wellhead and other surface equipment. And the cold CO2 condenses water and atmosphere, leading to reduced visibility. So in this here shows the unique characteristics of CO2. So CO2 can exist as a solid, liquid, or gas. And at the triple point, as shown here, all three phases exist in thermodynamic equilibrium. Along the solid gas line below the triple point, CO2 sublimes directly from solid to gas without going through the liquid phase. That's the sublimation point at 14.7 psi of CO2 vapor. Above the solid and liquid line, above the triple point, solid CO2 melts to a liquid. At the critical point, the liquid and gas states are indistinguishable and phase boundaries no longer exist. These attributes at the critical point and above, shown in the green area, is where CO2 is as a supercritical fluid. And that's the reason why your depths have to be generally greater than 1 kilometer in order to have the supercritical regime. So you have to take this in consideration: well and piping design, operations, well intervention. And usually the corrosion risk is less when the CO2 purity is dry. And the long-term stability of wellbore materials is complex. You got to incorporate material reservoir properties into your well design and completion programs. Now, what do we call life cycle governance? This is the ISO definition. And 16530-1. Basically, the well has 6 phases: the basis of design phase, the design phase, construction phase, operational phase, the intervention phase, and the abandonment phase. And all the elements that are common to all phases is well integrity, How do you manage it? How do you assess the risks? What is your organizational structure? What are the barriers? If they're compromised, how do you address them? And how do you verify the barriers? You're in continuous improvement and auditing. Complex load stresses on well integrity. So you always got to be aware of this. Impacts of corrosion on tubular cements, appropriate software and appropriate materials of construction. Minimize thermal cycling. Annual pressure monitoring is very important. Like I said before, loss of well control. You'll hear the term sustained casing pressure. Always monitor for that and take steps to do the diagnostics and address it if needed, because you don't want an uncontrolled loss of well-controlled situation to occur. Proper maintenance. Have good, complete data, user-friendly. Analyze the data and find out what are the reasons for loss of well integrity. And like I stated before, monitoring is very important. CO2 is not explosive, like I mentioned before. Fires are not a concern, but asphyxiation is, since CO2 is denser than air. So there was a mention in today's morning sessions about fault activation and fractures, etc. So it's very important. When you got high injection pressures with low injection fluid temperatures, can induce hydraulic fracturing. So you've got to have geomechanical models to determine the in situ stresses and the fault activation hazards. When you locate CO2 storage wells, locate them as far away from faults. So in your screening model, if there are faults, if there are fractures, those are not good sites for siting your CO2 storage wells. Why is a well a stressful environment? It could be due to the loads that are imposed during production injection, the temperature changes that take place during production injection, and during the abandonment phase, during well intervention phase, tectonic activity, formation changes that take place, or during completion, perforation, stimulation, hydraulic fracturing. So there's a lot of areas that cause stress on the well. During operations, then a whole bunch of challenges that occur due to well integrity, and a bunch of them are listed here, and I won't list them courtesy of Weatherford here, but it covers everything from casing wear and tear, cement channeling, pipe deformations, internal, external corrosion, metal loss, pitting, split collars, etc. Now, historically, when we designed a well, we were satisfied if it met the criteria of collapse, burst, tension, and axial compression, etc. But for CO2 storage wells, and also for the newer types of wells, whether they're deep water or HPHT, high pressure, high temperature, etc., you need appropriate software that will handle all the complex loads that are imposed. So you've got to have casing design, tubing design, comprehensive analysis. So some of the software you'll hear is WellCat, Drill Plan, or other companies may have proprietary in-house software. Drill design simulates flow and heat transfer during drilling. Production design simulates fluid and heat transfer during completion, production, stimulation, testing, and well servicing. And multi-string design predicts the pressure and volume changes due to trapped angular pressure and wellhead movement during the life of the well. So the tradition, if it was an onshore well, a straight hole, not a problem, but for the newer types of wells and CO2 storage, the thermal stresses, etc., and the corrosion aspects, so you need these sophisticated software in order to handle the complex loads during the life cycle of the well, not just during drilling. Now, it's very important to get a good primary cement job. If you don't get a good primary cement job during the original construction, you're playing catch up, and then it's a no-win situation. Cementing should be a simple, straightforward process, but why is it complicated? Basically, you're displacing cement in the annulus, and that should be it. But wellbore geometry, you got to have a straight annulus, no washouts, at least minimum 1.5 inch wide, always run a caliper. Centralization, have the casing in the middle of the wellbore, have a minimum 75% standoff. Circulate the mud before the cement job. Avoid the drilling fluid being static for an extended period. Complete displacement of the cement slurry. Displacement ends when the top plug lands on the float collar, what we call bumping the plug. If the plug does not bump after pumping the theoretical casing volume, and to avoid leaving a wet shoe is one that is surrounded by unset cement. Sometimes you have to add an additional half shoe track volume. Casing movement, reciprocation, rotation, or both. And then you've got to have accurate bottom hole circulating temperature and pressure for well control and cementing. So some of the software that is used by some of the service companies include SimCade, OptiSim, IntegraStar. So it's very important to cover all potential flow zones. Uncemented zones may not flow in short term, but may lead to sustained casing pressure over long term. Pressure tests, post-job information, and data from logging tools. Stresses on the cement sheet. You could have tensile cracks that occur. This courtesy of Kirksey here. Tensile cracks due to wellbore pressure increase or temperature increase, cement shrinkage. Debonding can occur either the cement or the rock interface due to the factors that are listed here, or they could occur at the steel cement interface. But in all these cases, what happens? You could have loss of well integrity, sustained casing pressure, or collapsed casing. What is sustained casing pressure? That is when you have pressure that builds up on your annulus, and when you bleed it off, it does not bleed off. It builds back up. So you know that you've got a problem on the backside, either due to influx of gas migration, a bad cement job, or some other problem that is causing the buildup of, and resulting in sustained casing pressure. So a lot of problems occur with well integrity in this area. Cement job evaluation. It's very important to look at a cement job, primary cement job holistically, right from even before you do the job out in the field, right from the lab analysis that is done in the lab before the cement is shipped out to the job site. And then once you're there, you got indirect methods and direct methods. Indirect methods, you got full returns you can monitor the mud tank volumes, and you know what the volume of mud returned during the cement job equals the volume of fluids that were pumped. And if not, you had lost returns or lost circulation. Lift pressure, you have a steady increase in pump pressure observed at the appropriate time after cement is pumped. Indicates the cement has turned the corner, is filling up the annulus and not being lost to the formation. And pressure generally increases because cement is heavier than mud. Then plug landed or bumped. You'll see a spike on the rig gauges, and when it happens at the expected time, you know that the plug landed properly and cement flowed out of the chute track into the annulus. Now, pressure testing techniques to confirm zonal isolation. Casing integrity test. Normally you test the casing to 2,500 to 3,000 PSI. Hold it for 30 minutes at typical quarter to 1 barrel per minute pump rates. If you get a straight line, you got a good test. Otherwise, you have a bad cement job. Leak-off test and formation pressure integrity test are basically the same, but one, you carry the pressure increase to the formation fracture point, and the second, you drill ahead, but not to fracture. But you always got to make this decision before you do the test, whether to carry it to fracture or not. And then finally, don't use info from straight holes to deviated holes and vice versa in the same field. A dry test is also known as inflow test, shows no downhole pressure change during the opening of the downhole valve or during the following shut-in period. And then you've got a lot of logs that you can run to evaluate: the ultrasonic imaging tool, the CAST-V, the UltraView, isolation scanner, etc. So the isolation scanner, the advantage is it can differentiate between different types of cements, light, heavy, and ultra foam, low density cements, etc. Cements for CO2 rich environments, specialty CO2 resistant cements. Evercrete is I think is a Schlumberger product, and others also have it. And then you have self-healing cements that are showing promise. Basically, the swelling allows the closure of microfissures and heals the cement sheet and reestablishes well integrity. You can use Class G cements too, but if you have to get approval from regulatory agencies, particularly here in the US, you may have, go the extra step in order to demonstrate well integrity. So a lot of factors go into getting a good cement job, right from the initial cement design and to the iteration that take place and the job that is executed in the field, at the job site, and the post-job evaluation, and the results of the isolation, and then the logs that are run and the client review. So you have the drilling engineer, cementing, petrophysicist, lab engineer, et cetera, in order to make sure that you get a good job, good primary cement job. Well design and construction, EOR, storage, CO2 are similar, but CO2 storage may be more stringent, especially we talked about CO2 resistant tubulars, metallurgy. Due to unique CO2 phase behavior, be aware of potential loss of well control. CO2 for storage, you're looking at, many decades of time frames. And complex loading conditions, we mentioned that earlier with WellCat, drill plan, appropriate software. Metallurgy, very important, for the corrosion resistant characteristics of CO2. Remember, we are looking at long-term storage. And then the requirements for the permit for post-closure monitoring after the well is P&A. For EOR wells, once the well is plugged and abandoned, your responsibility is met, but not for CO2 storage wells. So it's important to use appropriate metallurgy and the appropriate, materials of construction, whether they're cements, tubulars, etc. I'm introducing a term here, injectivity and regularity, even though that is not related to well integrity, because it's critical for the success of CCS project. For CO2 EOR, your objective is to maximize oil recovery, but for storage, you want to maximize your injection volumes and storage capacity, but with using the minimum number of wells. So injection can alter the rock properties by inducing chemical reactions. And injectivity loss factors could include wettability, trapping, salt halide precipitation, etc., as listed here. So what happens when you get salt precipitation or halide precipitation can cause major neo-wellbore injectivity loss, particularly in low permeability saline intervals. Asphaltenes can plug up plungers, clog wellheads, tubulars, etc. And I mentioned earlier, high injection pressures with low injection fluid temperatures can induce hydraulic fracturing. So you got to determine in situ stresses and fault activation hazards, and got to have geomechanical models and locate CO2 storage wells, etc. from faults. What is injection regularity? Is the ability to actually inject CO2 at the desired rates or quantities needed for, and this affects the project economics. We come to the final phase, the P&A phase. The quality for P&A is evaluated by the type of plugging material and plug placement techniques. And historically, of course, you had cements, but now with the the long-term 1,000-year timeframes, etc., new materials are being looked at. Bismuth alloys thermite that provide gas-tight seals. They've been tested in Oklahoma, Alaska, and the North Sea. The advantage of eutectic metal is it converts from liquid to solid when it cools and melts without going to the gel phase. Then you got the thermosetting polymers, resins. They're particle-free fluids which solidify into an impermeable material upon curing. And the curing process is temperature activated and occurs at a predetermined temperature. Resins have been used in North Sea and Gulf of Mexico, but they can lose strength downhole. They've also been used for sustained casing pressure and endless seal repairs. Then the placement techniques, the most popular one is the balanced plug method. But to have a successful P&A, you got to protect the environment, have downhole integrity, and be in compliance with the regulations. It's important to test the cement plugs after you've set it. So run the drill pipe and locate top of plug by applying weight after the plug has been allowed to set. A plug might be hard on top, but soft further down, allowing fluids to migrate. So testing after the plug has been set is important. So what are the imperatives of success in maintaining life cycle, not just during drilling, but through the entire life cycle of the well? Industry has the technology, knowledge, and experience. Implement best practices, appropriate well integrity testing, etc. Otherwise, you will not get the permit to social license to operate, and you want to avoid the problems as far as catastrophic loss of well control, safety, human health, environment is concerned. Thank you for your time, and I'll be happy to answer any questions.
Thank you so much, Mr. Talib, for the second presentation. It was also a great presentation. So I have in the chat another comment on the Insolar project. So Sufyan just mentioned that it was really a good presentation that has a lot of details and useful information, but the project of Insolar was not mentioned in the map. So if you want to add something to the previous comments on this project.
No, I'm very familiar with the Insolar project, but I just modified this to fit the time here for today's session. And, so yes, I'm very familiar with the Insolar project, and also, like I mentioned, the projects in Sleipner and Snow White. And also, I would refer also to the Petrobras project offshore Brazil too.
Thank you, Mr. Talib. So another question from Nashikat. He said, hello, Dr. Talib. A lot of research has been done focusing on well integrity with respect to the cement and CO2, the decarbonation of cement. So based on your knowledge and experience, what would you would recommend as research with respect to the CO2 and cement interactions?
Yes, a lot of research has been done on the compatibility of cements with CO2, and to ensure that the debonding does not take place. Remember one of the slides that I showed where the stresses caused the debonding either at the rock cement interface or at the steel cement interface. And that's what led to these newer types of CO2 resistant cements, like I mentioned, Evercrete and some of the other CO2 resistant cements that have taken place. But the question is, we don't have too much of operational history on exposure of cements to CO2 in real downhole well environments. So some of the wells are that we do have is with EOR in West Texas in the Permian Basin, because 70% of the world's CO2 floods have taken place in West Texas in the Permian Basin, going back to the 1950s. So when we recovered some cores from some of the wells that were exposed to CO2 over a 50-year period, we found that some of the cores were still intact, even though those wells were completed with Class G cement. So with CO2 for storage purposes, we don't have too much of history, long-term history, that is, exposure over a 30, 40, 50-year period. So some of that data is still being gathered. As we move ahead, we'll be able to get, besides what is determined in the lab, what the actual performance in the field is. Like I mentioned, here in the US, we only have one active well in Illinois, in Decatur, Illinois, in the Illinois Basin that belongs to Archer Daniel Midlands. And that's been in operation now about 5 years. We got in Insolar, in Sleipner, and then in Petrobras, and also the Gorgon field in Australia, a little bit longer, but nothing going back to about 30, 40, 50 years in order to make a definitive assessment. So, but based on lab studies, yes, we believe we got a pretty good handle, but the true test will be how will it perform in the field over long-term duration. The other question is, like I mentioned earlier, for EOR, once you plug the well, your responsibilities are met. But for a CO2 storage well, a class 6 well, you've got a post-injection monitoring period after the well has been plugged, which could run to a few years. And then you got another period which could run anywhere from another 12 to 20 years or up to a maximum of 50 years. So those cements have to, not degrade, not just during the life of the well, but have to show integrity even after the well has been plugged and abandoned. And we don't have information on that yet for strict storage wells for an extended period of time.
Okay, thank you so much, Mr. Talib. So Greg just mentioned that the latest copy of the CCS projects list in the EOGP is dated on April 2021. So thank you so much, Greg, for sharing the information. Another question from Reda, he said, instead to injecting CO2 underground, not sending it in space under minus 200 degrees, it will shrink in the vast universe. Can Elon Musk help us on that? Kidding. Okay. So he just proposed an idea if we don't inject the CO2 underground, but we can send it to the space. It was another idea from him.
Yeah, that's a very interesting question and relevant. So just to to inform everybody, that is also being looked at from what we call a space and terrestrial perspective. What can be done? Because right now, globally, I think we are generating about, we have to get rid of about maybe 35 billion tons per year or something. And what we're trying to do with the current is just a drop in the ocean. So in order to reach the targets of 1.5 or 2 degrees or whatever by 2050, 2070, all the CO2 that is being generated globally has to be captured and sequestered either terrestrially in space or in the subsurface. So one of the projects that is being looked at is how can this be captured from a terrestrial basis from the atmosphere itself. And I don't know whether this is the public domain or not, but I think there's some competition with big prizes that to be awarded for who can come up with the most innovative techniques to address this kind of situation.
Okay, we have
that is being looked at. It's a interesting and relevant question.
Okay, thank you so much, Mr. Talib. So we have another question from Mikael. So he said, can you give an example of what casing grades are being used for CO2 corrosion resistance?
I'm sorry, I didn't get that, Nadi.
Yeah, sorry. So I repeat. Mikael said, can you give an example of what casing grades are being used for CO2 corrosion resistance? The grades of the casing, yeah.
Casing, yes. See, strength is not really a problem, but some of the casing that are being used are L80, but with extra strength for CO2, and also N80. It depends upon what the depth is, and Regularity, for instance, is doing a lot of work on that on a global basis. I'm sure if you contact Regularity, they will, and they've got offices globally on some of the tubulars that they're looking at specifically for CO2. But it depends upon the well and what the characteristics are. If your CO2 is dry and does not have any other, impurities in it, and its mix-up is compared to acid gas, etc. So the metallurgy of that dictates what your casing is going to be. You have to be careful on how you're going to use 13 chromium or some other corrosion resistant alloys, and what the mix of molybdenum will be in it. So a detailed study has to be done for your particular stream of CO2 that's going to go down, and then tailor your tubular design to meet those requirements. But strength by itself, you don't need to have like P110 that you need for hydraulic fracturing, because in those instances, you're putting, maybe 10,000 PSI treatment pressure on your tubulars, and you've got to have high strength in order to handle that treatment pressures. Here, your pressures are not in that magnitude, but at the same time, they have to be corrosion resistant and handle the unique characteristics of CO2. Remember, if the thermal stresses that are caused are also, depending upon the temperature of the fluids and your CO2. Remember, in the phase behavior of CO2, it can be a solid, it can be a liquid, it can be a vapor, depending upon a supercritical, and the changes that take place in the phase behavior have to be addressed.
Thank you so much, Mr. Talib. So another question from Nididi. She said, or he said that, does CO2 EOR give rise to adverse mobility ratio problems resulting in excessive channeling and oil bypass?
Yeah, for CO2 EOR, you want to make sure that your mobility ratio is 1 and above, positive. But again, the screening that has to be done is very critical in order to make sure that your EOR project is a success with CO2. And remember also, we got water alternating gas. So in many CO2 floods, just putting CO2 by itself is not that successful. You have to use a WAG process where you alternate a slug of water and then a slug of CO2. And that was presented by Parag earlier this morning, what Oxy is doing in their operations. So you have to look at a lot of screening factors that have to go back. And for instance, in many reservoirs, in many places, you may have CO2, but it won't be, a success.
Sorry about that.
No worries. So just because you got CO2 does not mean that you're going to have a success in every place where you flood it.
Mm-hmm. Thank you, Mr. Talib. So another question from Safian. He said, you mentioned earlier something about well trajectory. So do we need to drill horizontal wells vertical or horizontal to the minimum horizontal stresses? And if this will create transverse or longitudinal fractures?
Yeah, that is also a very good question. See, when we are looking at capacity, okay, one of the things that is being looked at is, if we drill a horizontal well, will we have more capacity to put CO2 away compared to a straight vertical well? But then there are other issues that come up as far as fractures that are concerned, and what because containment of CO2 is critical. So that's the reason why you're not allowed to operate above the frac gradient. If your frac gradient is, let's say 0.8 PSI per foot or whatever it is, you're only allowed to inject maybe at 90% of that, 80% of that. So anytime you have fractures or you have faults, especially if you got concern about them being reactivated, all those fractures becoming transmissive or pathways, that is looked at, closely. And that depends upon how good of a cap rock you are and at what depth you're completing the well and where your cap rock is as far as the vertical separation is concerned. So it has been looked at, for horizontal wells in order to increase capacity. And in certain places, if all the other factors fall into place, that may be one option. Especially if you got, a low permeability saline aquifer and it just won't meet your design targets. Because let's say you want to put 1 million tons per year away in one location, and the characteristics are not good for you to complete the well. And it depends on what type of formation you are. Is it tight formation or is it? So generally we screen it out. You want good permeability, good porosity, good KH values, But at the same time, if you've got a multi-layered system, sometimes that's an advantage because you can put away in different layers, and the potential to transverse and intersect and cross multiple layers becomes less of a concern. So from a well integrity perspective, that is a plus. So it depends, are you in a sandstone or in a carbonate, dolomite type of reservoir, and what the characteristics are, and what your rates are, and all those have to be looked at in a holistic fashion before you can make a decision.
Okay, thank you, Mr. Talib. So we move to another question. He said, Mr. Talib, how would you balance the need for running a fiber with the imperative for getting a good primary cement job?
Yeah, see, a fiber optic is playing a bigger and bigger role. In the past, it was quite expensive. And also what happened is once the fiber optic had some problems downhole, then you were not able to get good information later on. And since it was expensive, mostly it was used in deep water wells where the importance of getting data in real time was very important. But now it is being used both, you got distributed temperature sensing, DTS, as well as DAS, distributed acoustic sensors that are being used for to transmit, in real time information. So that is a very valid tool that is being widely used now. And mostly I think new wells that are going in, they're going to have that because you can get real time information and take corrective steps before any problem occurs. And the cost, there was some question in this morning session of what the cost will be for a class 6 well. Depending upon the depth of the well, let's say it's about, say, 6,000 to 8,000 feet. The well cost can be anywhere from 2 to 5 million. And it depends. So now if you add DTS, DAS for monitoring and all the other things, that's where the cost goes up. If you're a horizontal well, obviously the cost will be, again, higher, but then the number of horizontal wells may be less than the number of vertical wells that you're needing. So for a storage well, you want to maximize your injection rates they're putting in with the least number of wells, with minimum number of wells. So you're looking at all these different aspects and how can I increase my capacity, my injection capacity with minimum number of wells.
Thank you. So for the last question, Dusty just asked, the CO2 is hard on steel. So the HDPE application for CO2 inside of the steel pipe, like your comment about that.
Yes, see, fiberglass and fiberglass reinforced, epoxy, they're also being looked at for CO because they got good corrosion resistance, but they don't have the same mechanical strength properties. So it's a balance between, okay, I need good mechanical strength properties. At the same time, I want corrosion resistance. So if you don't, if you strictly want corrosion resistance and don't have strength concerns, then fiberglass is okay. But for CO2, for storage purposes, again, integrity is so important, not just during the life of the well. You got to show integrity during the drilling phase, during the operations phase. And remember, every time there's a change in the status of the well, let's say you got a workover or well intervention, the barriers get impacted. So you got to go back and verify that the barriers are intact. And if they're not, you got to take steps in order to ensure that the barriers are there, right? Well integrity barriers, always you got to have a minimum of 2 barriers throughout the life of the well. And what is one barrier? Okay, that is during the drilling phase, you got the hydrostatic mud that is present, your steel, your cement. So anytime those barriers get impacted, you got to do a whole study from a risk assessment to make sure that they are restored before you can go on to the next phase. Then you got the plugging and abandonment phase. And then you got the post-closure phase. Remember we talked about that the cement and all the downhole tubulars have to show integrity even later on, not until they are plugged and abandoned. So all these factors are being looked at, and we don't have too much history. That's the biggest thing globally. We're still collecting all the data. We're adding more to our database, but we don't have a 50-year history of operational performance. so that we can go back and recalibrate and history match and match performance with what we had predicted.
Okay, so that was the end of this presentation. I will stop recording. Thank you